We define a binary search tree as a binary tree where every node is greater than all nodes in the left subtree and smaller than all nodes in the right subtree. And given a binary tree, we want to check if it's a binary search tree. A common solution to this problem that a lot of people think of is to check if the actual node is greater than the left child, smaller than the right child, and that both subtrees are also BSTs. But this solution doesn't always work. Checking that the node is greater than its left child is not enough. It has to be greater than all the nodes in the left subtree. Same issue with the right side. And even if we're doing it recursively, we can have cases where even if the node is greater than its left child, but it's not greater than all remaining nodes in the left subtree. Little example here, 5 is greater than 2 and 2 is smaller than 8, so our solution would return true. But this tree is not a binary search tree because 5 is not greater than 8, which has to be the case in a BST because 5 should be greater than all the nodes in its left subtree. Okay, so what's the solution then? The idea is that each node has to be in a certain range of values, because when we go to the left, the value of the actual node becomes the upper limit, because all the nodes in the left subtree must be smaller than the actual node. And when we go to the right, the value of the actual node becomes the lower limit, because all the nodes in the right subtree must be greater than the actual node. So while traversing the tree this way, if we find a node whose the value is not in the required range, we return false, because it would mean that the binary search tree condition is not respected. Let me show you an example. The root doesn't need to respect a certain range, it can have any value. Now when going to the left, 15 becomes the maximum value. 8 respects the range, so we continue, we call to the left, and 8 becomes the upper limit. 4 respects the range and it has no children, so we return true and we backtrack. Now when going to the right, 8 becomes the lower limit, because nodes in the right subtree must all be smaller than it. 12 respects the range, we go to the left, 12 becomes the upper limit. 10 respects the range and it's a leaf, we return true. From the right, 12 becomes the lower limit, and 14 respects the range, we return true. Both subtrees return true, so we also return true. Same thing here, both subtrees are BSTs, we return true. Back to the initial function call, now we need to go to the right, 15 becomes the lower limit this time. 22 respects the range, so we check subtrees. We start with the left one, 18 is between 15 and 22, so it respects the range. We go to the left with 18 as upper limit. Here you can see that 13 doesn't respect the range, it's not greater than 15, which is necessary because it's in the right subtree of the root whose the value is 15, so we return false. Then we directly return false here, here, and here without checking all the nodes because we already know that this tree is not a BST. We can notice that we were working with two variables minval and maxval that represent the range that has to be respected by the actual node. So in code, in addition to the root, we will have two other parameters minval and maxval, whose the initial value is -infinity and infinity respectively because the root doesn't need to respect any particular range, it can be anything. Now we have two base cases, the case where the tree is empty and the case where the actual node doesn't respect the range. When the tree is empty, then it's considered as a BST because we don't have something that breaks the condition, so we return true. And when the actual node is not between minval and maxval, then the BST condition is broken, we return false. And in the recursive case, we just need to check that both subtrees are BSTs, but when calling on the left subtree, root.val, which is the value of the actual node, becomes the new maxval. And when calling on the right subtree, root.val becomes the new minval, as explained earlier. This solution has an O of n time complexity where n is the number of nodes in the tree because we're traversing the whole tree, and an O of h space complexity where h is the height of the tree because of the call stack size. This one was the first solution, but we also have another interesting solution. You have to know that when traversing a binary search tree in order, we get strictly increasing values as you can see. So the idea of this second solution is to perform an Inorder traversal while storing the values in an array, then we just need to check if that array is strictly increasing. An Inorder traversal is to traverse the left subtree, process the actual node by adding its value to the array in our case, then traverse the right subtree. Now in the isBST function, we create an array vals, we call the Inorder function to fill it, then we just traverse it to check if it's strictly increasing or not. If we find a value that is smaller than or equal to the previous one, we return false. This solution has an O of n time complexity because we're traversing the whole tree, and an O of n space complexity because we're storing the values of the n nodes in an array. We reached the end of this video. I hope that you now know how to check if a tree is a BST with both methods. Check my other tree related videos, like and subscribe to the channel, and see you in the next one.